So last class we looked at the timing constraints max and min, and today we'll look at the impact of clock jitter as well as pulse clocking technique. So one of the things we considered last class was the impact of clock skew on the max and min constraints. Basically, it kind of makes life harder. So whether it comes in the positive sign or negative sign, the rule of thumb is you use the sign which makes your life harder as a designer. Okay, so you kind of use that thumb rule. And really the problem comes because of the mismatch in delays of the clock edges. See, you have a clock source in the chip which supplies these clock edges to all the sequencing elements in the chip, and they're all spread out spatially, right? A chip is pretty large and sequencing elements are all over the chip. So there is an edges are created periodically by this clock source, and these edges propagate down. So skew is basically the difference in the propagation time. Of course, this portion is common, so there is no issue, but from here there is a splitting, the red and the blue. The paths are different. And to the extent that, for example, the loads here, symbolically I've just shown one flop, but you can imagine there are a bunch of flops on this side, bunch of flops on this side, and all over the place. The loading could be different, the wiring lengths could be different, capacitances could be different, and so on. And so the job of the clock tree designer, the clock distribution network designer, is to ensure that the delays are matched as much as possible. And the delays are calculated based on whatever we have learned so far earlier in the course. The delay is proportional to the load, inversely proportional to the width, the sizes, etc. So use that to adjust the delays by just kind of like how you do wheel balancing for your tire of your scooter or your car. Like you have to keep adjusting some weights here and there. So kind of like that is done. Of course, this is very complex to do by hand because the size, the number of flops is just too large. So it's all kind of done basically in an automated way by these clock tree synthesis tools. And what we basically saw was that if you look at the max delay constraint, when a launching flop launches the data takes a time TPCQ, propagation delay from clock to Q. It goes through the combinational logic with a TPD, and then it has to be ready by a time T setup before the next clock edge. Because if it violates the T setup time, if you recall the setup and hold that figure which had the shape of a funnel, the setup time is a time at which, if the data arrives at that time, the delay of the flop degrades by about 5% to what it would if it had come much earlier. So if it violates the setup and comes even later than that, then the PCQ starts becoming more and more, and at some point the flop can also fail to capture the data correctly. Forget about the large delay, it can also fail to capture it correctly. So one needs to make sure that the setup time is met. So of course what skew does is, you could have a situation where the clock, instead of being here, this clock edge, it comes a little earlier. Maybe the distribution tree and the path is such that the delay from the clock source to this edge, this node, is less than the delay from the clock source to this node. So you have a skew where this comes a little earlier, and so the effective timing between this edge and this edge is reduced by the amount T skew. So what you have is TPCQ plus TPD has to be at most clock period minus setup minus T skew. So when you do your circuit design and you say I want to meet a certain speed of a gigahertz or whatever, so gigahertz means a 1 nanosecond, you will have a setup time maybe of 100 picosecond, let's say, and then you have a certain budget of T skew. How do you have a budget of T skew? Maybe based on prior experience, people will say, okay, maybe you can budget about 100 picoseconds of clock speed. So from 1 nanosecond you have lost, from 1000 picoseconds you have lost 200 picoseconds. 100 for setup, 100 for skew. So you are left with 800 picoseconds. So you are allowed only 800 picoseconds of time in which to do your job, of which again maybe another 100 picoseconds is lost for P, C to Q. I'm throwing out these numbers 100 picosecond. It's, of course, it's not, it depends on the process technology, right? The fan out 4 delay in a, for example, in a 14 nanometer process will be maybe about 5 picoseconds. So you can expect propagation delay clock to Q also of the order of a fan out 4 delay. Okay, a setup time also of the order of a fan out 4 delay, and perhaps Q also maybe a few fan out 4 delays. Again, it depends on how well you control. So in that case, yeah, of 1000 picoseconds, you lose out maybe about 15-20 picoseconds for all these overheads. Of course, if you fail to meet this timing, that means you have logic. Maybe you did your, let us take your FPGA design which you did, and you have all these paths, and it just happens to be, the delay happens to be more than what this constraint allows. So then what do you do? Well, you have to kind of go back, and you can try very hard to try to reduce the delay by looking at sizing, looking at layout, maybe make things closer. You have to do those kinds of things. If not, you just have to let go of the TC and say, okay, my TC is going to be a little larger because I'm not able to meet. Similarly, we saw the impact on min delay, right? Because when you have the clock on the receiving flop, there is a hold time requirement. That means you cannot change the data for at least a certain minimum period of time. That is the hold time. If it changes, then the flop may not get the data correct. So what that means is when the data is launched from this flop, it better not come and corrupt the data which is supposed to be captured in the same edge. It has to, it should not come urgently out here. So there is a minimum delay. That is from T, the minimum delay of clock to Q and the logic path delay has to be at least the whole time plus the skew. Why? Because what if this clock happened a little later, this edge? Okay, maybe from the source, the delay to this node versus source to delay to this node for the clock is different, and this is a little slower. So that means it takes a little longer to capture. So this better be slower. So that's why skew comes on this side. It has to be at least T hold plus T skew. Now so how do you distribute these clocks such that you have a minimum skew? So imagine that you have a clock's source out here at the center of the chip. So one approach is, say, some kind of symmetry. We try to make things symmetric. So in that spirit, this kind of architecture was evolved. This is called the H tree, because you see there are all H's. There is a big H out here, because what this does is when a clock comes in here, the 4 leaf nodes, this leaf node, this leaf node, this leaf node, this leaf node, all of them are equidistant from the center out here. They are equal path lengths. So the wire lengths are the same. So resistance and capacitance is the same. The same amount of buffering, what you put 4 buffers, all of them are the same. So you would expect the delay to be same by symmetry. Okay, so that is one important principle, is to use symmetry to try to match things. So now you can repeat the same thing. So when you come here, again you have another edge to distribute it like this. So now from here the information goes to these 4 leaf with equal delays, and similarly out here, and now the delay from here to the next level leaf here is the same throughout, and so on. So then again from here, if you want to distribute, you have one more edge. So you see it's like a self-similar kind of fractal type design, right? So this is what is called a H tree, where you have from the center, so maybe the clock source is sitting somewhere here, you get it out here, inject it out here into your clock distribution network, clock distribution tree, whatever you want to call it, right? Of course, in reality what happens is things are much messier, because the loadings are not the same. What if there are more flops here than here, than this side? Okay, up to this point it seemed to be same, but actual loading at the end of the leaves are very different. So so just this will not guarantee that. So what happens is that the tools will go ahead and kind of start mucking around and really adjusting the path lengths, etc. So you get this really messy modified H tree, which is a picture from the Itanium processor. Okay, so this kind of modification is happens, as I said, in an automated way by the tools. It's kind of very difficult to do it manually. Okay. But what happens is just delay calculation. You have to keep calculating the delay and keep adjusting the delays and make sure the delay from the source of the clock to the input of the flops, the clock input of the flop is the same for all the flops. Okay, that is basically the requirement to ensure you have no skew. Here is another approach. What is done here is what are called spines. So spines are used. This was used in another processor, where from here you have a balance tree which comes here. Okay, it's not like a H, but there is balance, and then from here again it splits into two, and then from here it splits to. From here it goes to the top spine, bottom spine, and then the center spine, sorry, and so on. And then finally it comes here. So it may not be very apparent, but again from the PLL to the each of the, so what these are local clock. So the clock distribution is broken up into two pieces: a global clock distribution network and a local distribution network. Global is coming here and reaching to the regions. You break up the chip into regions, and then you go to that region. For example, you know, here this is the global clock distribution. It comes all the way to this region, and once it gets to this region, there is a local distribution out here, which is in this case happens to be same like an H tree. So it's kind of similar out here. So you come and local from here again there are some buffers etc. which drive the clock to the local regions out here. So global clock and then local clock, and you see the layout out here. These are the spines, where there are a lot of these buffers, you know, basically this structure, all these structures are there, including this big fat metal. You see there is this thing out here, it's all shorted. You see these clock buffers are all driving this horizontal line out here. It's just a big fat metal line, just running from left to right. It's very wide, very low resistance, and it's being driven in parallel from all these different, spatially different regions, so that the skew across here is kept almost close to zero, because it's being excited from multiple different spatial points along this horizontal line from here, 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 here in parallel. And the resistances are also kept, use very wide wires, so the resistance are very small, so that the relative skew out here horizontally is kept very small. Same for this one and same for this one. If there is a between these guys, so what happens is that when the signals come, firstly by what they do out here is that they make sure that the arrival time of the edges at these different points is kept as same, you know, as close to zero as the difference should be kept as close to zero. They arrive almost at the same time, but there will always be mismatch in the paths, and they will be off by a little bit. What that does is that the effective edge out here becomes an averaged edge. Okay, so you have one edge comes a little early, one comes a little late. The actual signal out here would be an interpolation between the two. Okay, so that's kind of what happens. So you have an effective edge which happens on this node, which is in between. It's an average of the arrival time of the edges at all of these nodes. Pardon? Pulse width will not be done. The rise time will degrade a little bit, because let us say you have one edge coming here and one edge coming here a little later. Okay, let us say the rise time of the first edge is maybe 10 picoseconds, the second is 10 picoseconds, but there is a little spacing between the two of maybe, you know, 5 picoseconds. Then the effective edge rate at this point will be in between the two edges. The midpoint will be in between the two midpoints. You can imagine that you have a ramp, two ramps, and then the output will start from the bottom of the first ramp and end in the top of the second ramp. So the midpoint will be between the two midpoints, but the edge rate will be also less. I mean, it will rise slower. So that is the degradation which happens, but everything gets, the midpoint delay gets averaged out. So this is the big, there will be big fat metal wires out here, which is what it is. So this is one approach. Yeah. There is a single PLL, of course. Yes, there is a single PLL. Correct. So the important thing is from this PLL to the spines, the three spines, the delays will be the same. And that delay, distance need not be the same, delay will be the same. Exactly. You see these buffer tree they have shown already, right? This is the how they are buffering it. So if you can have, it's been done very carefully such that the delay from this to these three spines is the same. Yeah, because if you see out here, from here it comes here, and then from here it is sent to this, and then back to this at the center. They don't tap it from here, they tap it from here. So there's extra delay because from here to this there's extra wiring delay. So to excite this spine, they don't tap it locally, but they'll get it from this side. So that's why they're matching the delay from the PLL to all the three spines, and within the spine, because it's horizontal and excited spatially from all along the horizontal simultaneously, the delay across the spine is also kept very small. So so in fact the lowest clock skew is achieved, and this is kind of done in extreme cases when you really want to keep the clock skew very small, is to actually have a large metal grid. Just take this concept of these horizontal spines, sorry, not here, and imagine that you have this grid of horizontal and vertical wires, and all of them are shorted together, and you have this grid, and this grid is it's like one large, very low impedance. Maybe you make it with very fat wires, very wide, and layers from wires from a upper layer in the process. So they are also very thick. So you have very low impedance. Remember delay. So the RC delay due to the wires and skews due to the RC delay is basically almost eliminated. So then you have this large grid all across the chip, which gets excited just like the same approach you might have like a H tree or something to excite it simultaneously from all points in the grid. Okay, and then you have the whole grid going up and down. So that gives you the lowest skew, but that is also the most power consuming approach. So some early chips they did that, but then they consume so much power. So because you just are having this large metal grid which is kind of going up and charging and discharging at the clock rate, like few gigahertz. So that's why the clock power consumption is quite high, and people look at various techniques. So they break it up into global clock distribution, which is what we are seeing, and then local clock distribution. Local clock distribution we'll just see in the next slide. You can do clock gating. We studied clock gating in one of the earlier classes. So you can shut off clocks. Global clock has to keep on happening. Maybe you shut off the global clock when the whole chip doesn't need to work by shutting off the PLL or doing something. But there are also other techniques which unfortunately we can't go into due to shortage of time, but people have explored various other techniques to reduce power consumption in the global clock distribution. So one approach could be reduce voltage swings. So the global clock could be clock signal which has lower swing clocks. Another approach could be maybe it runs at half the clock rate, and then when it comes to the local one there is a clock doubling. So this structure, this logic circuit doubles the clock, where the global clock is running at half the rate and you get both edges, you get this thing. So you can just work through the logic later on to see how it works. Okay, so so that could be another approach. So the global clock now is running at half the clock frequency. So the local clock out here, sorry, in these boxes, that is what we are looking at here. It could be a simple buffer, is just a couple of inverters to drive out and drive a small local region. It could be buffers with enable, so that you can do clock gating of that region. So enable comes, and then you only if the enable is high, the clock is fed through. And the thing is that sometimes you also, if you remember some of the flops, you also want clock and clock bar, right? And you want to make sure the clock and clock bar delays are kind of matched. So you are forced to have different number of inverters in the two paths, right? Because one is the logical inversion of the other. So when you have So you have the global clock, you have maybe even number of inverters to get my clock and odd number to get my clock bar, but you still need to match the delays. Okay, and that you can match by adjusting the sizing out here. So you can, just like what when we discussed in the SRAM timing generation, I said you look at the pull-ups and pull-downs and you match the two and so on. So you can do something similar out here, where when the global clock goes high by a pull-down here and a pull-up here. Similarly, there is a pull-down, pull-up and pull-down here. So 2 pull-downs plus 1 pull-up has to match to 1 pull-up and 1 pull-down. And that you can set up the equations, and based on the loading you can kind of go back and try to calculate the sizing and so on and get the delays to be the same. Now there is one more component to this clock distribution, one more non-ideality rather, which is what is called clock jitter. Jitter is essentially something where the clock edge is not stable and it keeps on kind of moving around. Of course, in what sense, right? So if you look at the clock is periodic, right? So you take every period and kind of, when you draw the graph, you just put it laid back, overlaid on itself. Okay, because so imagine that the next period edge also lies on the same one. So you get an overlay diagram, right? That's what you get when you look at this in an oscilloscope. Imagine that you have an ideal clock. You trigger the oscilloscope and look at your clock, the actual clock. You'll find if the actual clock had exactly the same period all the time, it will lie exactly, you'll just get a straight line like this in the oscilloscope. But what happens is that because of there is something called jitter, you'll find the clock edge sometimes happening earlier, sometimes happening later. That means the period of the clock on an average is Tc, but cycle to cycle there can be small variations. It can be a little less than Tc, it can be bigger than Tc, it will keep on kind of fluctuating. Okay, it's a statistical process, it's a random variable. The clock period is a random variable. So this is basically what happens. It is, no, there is a difference between drift and randomness. So drift implies a frequency change. So here what we are saying is the clock frequency is say 1 gigahertz. Okay, the frequency is not changing, it is 1 gigahertz. But so that means you expect the cycle to be 1000 picoseconds. But if you measure the cycle, every cycle you keep measuring, over a period of time you observe the cycles and imagine magically somehow you could measure it. You will find that the cycle is not exactly 1000 every cycle. It might be 999, 998, 999, 1000, 1001, 1002, 1003, back. It will keep on fluctuating. That is what when you observe that in the scope, you will see that the edges keep on fluctuating. On an average, it will be 1000. So there is no drift. Drift means the frequency is a little bit off. It's not exactly 1 gigahertz, but 1 gigahertz plus 0.1 or something. Then the frequency is a little different, so it will slowly walk off. We are not talking about that. The frequency is controlled, but you will still find this randomness in the period called cycle to cycle jitter. Okay, so so this technical definition, so basically there is kind of there are two ways of looking at this. There is what is called cycle to cycle jitter. That means I have one cycle, there is some period, next cycle there is a slightly different period and so on. So that is cycle to cycle jitter. Okay, period jitter is I have an ideal clock and I am comparing my period of my clock to that ideal clock. Now for digital timing closure and so on, the cycle to cycle is important. Why? Because my edge launches the signal, the next edge in the cycle captures it, which launches for the next and so on. So the cycle to cycle variation is very important because my period is fluctuating. So when you look at the way this is characterized is by a histogram. What is this histogram? So you have the ideal edge, say happening at time 0, and then the actual edge. Remember this modulo, the clock period. We are looking at the edges, multiples of clock period. So edge at exactly the clock period happens at 0. Edge slightly more than clock period happens a little bit later in the positive side. if it's less, it happens in the negative slide. So you collect a histogram. That means you break it up into bins. In oscilloscope, you can see, you can break it up into time bins, maybe 1 picosecond bins, and see how many times the edges happen here, here, here. You'll get a distribution like this. Okay, again, it depends on the clock, the jitter statistics. You know, it could be saying unimodal, it could be bimodal, etc. So typically it is unimodal. It can maybe approximate, you can approximate it as a Gaussian, and so it will have a standard deviation. Okay, standard deviation is basically the average average distance of the clock from the center. So that is sigma RMS. There will be some jitter number. It will be in picoseconds. And so now when you budget, say you're looking at the cycle to cycle and you look back to your timing analysis, you have to kind of, you can, you know, say the launching clock was here maybe perhaps, and the arriving clock happened maybe a little earlier. So you might have to budget for some multiple of sigma as the timing jitter. Okay, so depending on, so maybe plus minus 3 sigma, or T jitter maybe say 3 sigma or 6 sigma. So so now you can say, you know, why is this jitter happening, right? So so you have basically two components to the clock distribution. There is the clock source, and then there is the clock distribution network. The clock source itself could have a jitter. Okay, so that jitter turns out to be usually quite small, but also if you see, the clock edges are moving through this path, and all these paths, the delays, whenever there is a change, a fluctuation of the delay, you will have a jitter. The delay of a logic gate, of a buffer, if it's always constant, then there is no issue. But if it changes with time, now why will the delay change with time? The biggest cause for the change in digital circuits turns out to be noise from the power supply, because delay is a strong function of the power supply. You have already seen that, right? The delay, if you reduce the power supply, it degrades and becomes small. Now power supply is a very noisy node. It can kind of fluctuate quite a bit. So whenever power supply fluctuates, dVDD, then the delay will change by, if F is the relationship between delay and VDD, then d delta delay change is derivative of F times delta VDD change. Right. So that is basically also saying, if I want, so, and this, so that means this will fluctuate, this will fluctuate, this will fluctuate. Now one of the things is, any fluctuations in delay out here is seen by both the nodes C1 and C2. So C1 and C2 both will move together because of fluctuations in D. So they are correlated variations, correlated jitter, which you don't get too much. If C1 launches a data and is captured by C2 and C1 gets delayed, C2 will also get delayed. So there is no problem. But any uncorrelated jitter is what you have to put into your timing budget analysis. And so your timing max delay essentially becomes constrained by not only period from which you take out setup skew, you also have to take out any uncorrelated jitter component. Okay, so again, if you see, then you know you have low, you make sure your sizes are large, because there is a thermal noise. Thermal noise you can reduce by increasing the sizes of devices. And in addition, your clock distribution, you try to have very clean supply as much as possible, or make delay cells which are less sensitive to power supply, and so on. So that's how you get. And the other thing also is the edge rate of the clocks. If the edge rate is very poor, remember, as we discussed in the last class, any change in the voltage side leads to a larger change in the timing side. So again, you want to have sharp edges to reduce the timing jitter. Yeah. Yeah. No. So what I'm saying is, if I look at the arrival time of the clocks at these nodes, if I just observe any particular node, and if I had a way of measuring the jitter of that node with respect to an ideal clock edge, I'll see some amount of jitter. Similarly, in another node, I'll see some amount of jitter. Now, one conservative approach is to say, look, my total jitter is kind of, if both these are uncorrelated, then the total jitter will be, which I will use for my thing, is not summation but RMS summation. Okay, RMS summation of the two will give me the effective jitter between these two nodes, and I'm going to use that. But that could be very conservative, because if both C1 and C2 are, say, completely correlated, then relatively there is no effect. The jitter is completely gone. There is, even though because they are both moving together up and down, so it will not affect the timing constraint. So that is basically all I'm saying for timing constraint. Pardon? Not necessarily, because what happens is that is true. See, here I've shown it like this, but see, these two flops could be in two different parts of the chip. It could happen that if you look out here, there is a signal from this side, from this launching flop, which is captured by a receiving flop on this side, and they are pretty far apart spatially. So the local VDD changes could be quite different between the two, right? So they could be uncorrelated. So that is, it also kind of brings out another important thing, that is, you can now define global and local skew and jitter. If you really want to, like, locally skew might be small. So if I have a local launching flop and a local capture flop, skew will be small, whereas a global, it could be larger. So you can kind of do much finer timing analysis by taking into account all these kinds of aspects. It is basically, it's just done. Really, what is done is kind of like this. Some budgets are given, and conservative budgets for jitter and skew, and you kind of, when you do timing analysis or timing closure, you use that, and then when you do clock tree design, you design the clock tree and try to meet the skew targets by adjusting the sizes and so on. And in terms of jitter, it's kind of very difficult to upfront design. I really don't think anyone in their design analysis at that point they're analyzing the jitter, as opposed to just once they have the chip and with historical data they know what kind of jitter they can expect, and with some thumb rules they'll come up with these jitter numbers and say, let's use those numbers for our timing closure. And it can happen that you can be quite conservative, and people have also found that sometimes the skew numbers and jitter numbers they use are very conservative, and there is much more margin. So how to tighten that up and improve it, it's definitely an open area in some sense. Yeah.
Then the effect of jitter on that depends on where the data is coming. For one clock, the data is coming in sync with the jitter clock, and for another clock, the data is coming in sync with the actual clock.
No. See, if you see out here, say C1 launches the data and C2 captures. Okay, if C1 got delayed due to a small arrival time of C1 got delayed due to jitter, and C2 also got delayed by the same amount, then when C1 launches and C2 captures, both are shifted by the same amount. See, it's when they are uncorrelated, when C1 launches little later and C2 comes little earlier, sometimes then you have a problem.
The data for this is being transferred,
right.
Data for the other is being taken from other data.
So you have to, that's right. So if that is uncorrelated with this, then it will be a problem. You have to take that into account. So if you, in this kind of analysis, what you do is you look at pairs. You have to analyze for every pair. You have to do timing analysis for every source and sink. Data is also jittered because data which is launched from the clock is synchronous with the clock edge, right? So nowadays the simulation tools have, the models have become pretty good, so you can predict the jitter quite reasonably well in your simulation. As I said, if there are multiple components out here. So one component is the inherent. If you take, at the end of the day, oscillators will be, let's say typically in digital design there will be ring oscillators. Remember, we have already seen a ring oscillator. odd number of stages, you loop it back. So the period of that ring oscillator is determined by the propagation delay, and so propagation delay is determined by the current and the capacitance, load capacitance and the current. So capacitance is something fixed and you calculate, and it doesn't change with time. But the currents can, every time there is a charging discharging event, the current, at the end of the day, if you really look into it, there will be a noise component to the current, thermal noise, right? So you'll have some mean current and some small fluctuation in the current, and that fluctuation will change every time with time. So that is characterized with, so that can be modeled, and it's kind of models, people have now done a lot of work and they know what is the thermal noise component. So if you take such an oscillator, then the inherent noise of that can be characterized. Similarly, it will be locked to a reference noise is characterized, and so on. So that portion can be simulated, and then when it goes through a clock distribution network, then as I said, really the clock distribution network adds a certain jitter which is related to noise in the power supply. So it really comes down to how well you design a power supply network. If a power supply network is very noisy, it will lead to a lot of jitter and noise in the clock distribution network also. So they're all tied together, it's all related. But you can put a budget, you can say that, look, my power supply, I don't want to fluctuate by more than 5%. Now typically 5% change in supply leads to 5% change in delay. So like that you can kind of come up with ballpark estimates as to what the variation in delay will be. Okay, and you can also do more detailed simulations of a clock tree network to kind of get the, if you put in a fluctuation in supply, how much fluctuation there is in the delays. You can also do that. But basically, but then you have to make sure that you control the power supply fluctuations. You push the problem to good power supply design. Also you have substrate noise, I have kind of ignored that, but substrate, any fluctuation in the substrate potential will also cause a change in the threshold voltage, will cause a change in the delay. Right. Coupling, if I have another signal out here running, remember we discussed when we talked about coupling, aggressor, victims and so on, if signals are going the same direction, the effective capacitance is less. If they're going in opposite direction, capacitance is more. So that could also lead to fluctuations in the delay. So all these factors are there. So it kind of makes it very complex to precisely get a number during simulation. So usually based on experience and some simulations, some conservative numbers are put for these parameters. So similarly, min delay, uncorrelated jitter, say the launching and capturing, if it's a little different, that uncorrelated jitter will affect the min delay also. Okay, min delay has to be at least hold plus Q plus the jitter number. So, people for very high performance design have started using these pulse clock based designs, where what you use is, instead of a flop, you use a latch. A flop has two latches, master and slave. You just remove one of them. You just use a single latch. That's all it is. Okay. Except the clock is now a pulse, short pulse. Normally a clock will be a 50% duty cycle. That means 50% of the time of the clock period it will be high, 50% it will be low. Whereas for a pulse clock it will be much smaller, maybe 10% duty cycle or even 5%. Right? It will be a narrow pulse. This is how the pulse clock works. So the main reason is to reduce the overheads. Instead of having two latches, you have one latch. So the sequencing overhead is reduced with pulse clocking, and you can have much faster operation. Because if you go back to this, TCQ, T setup, these are all kind of overheads related to the sequencing element. They are eating away margin from your clock period. In very high performance designs, if you recall, we said the clock period will be about 12 fan out 4 delays. If you lose like a fan out 4 to clock Q, another fan out 4 to clock setup, I mean you just lost 2 out of 12 just for going in and coming out of a flop, right? So that is a lot of overhead. So clocking becomes, clock distribution, sequencing, choosing the right clock becomes very important for very high performance designs. So that is why people started using pulse clocks. because there is a single latch. Now the max delay, min delay constraints for pulse clock can be a little confusing. Okay, how do you come to that? So the way I like to think about it is the following way. So what you can think of is kind of an oscillatory type circuit. There's a single pulse latch, and you can use it for latch based design, flop based design, all of that. This kind of approach to understand what's going on. Basically what I'm showing out here is the latch output goes through the combinational logic and comes back. It's a cycle. Okay, and I'm showing a knob out here. I'm just showing this an arrow out here where I can adjust the delay of the combinational logic. I'll start off with a very low delay and I'll keep on cranking the delay till the circuit fails. And really what I will have is, maybe I have an inversion out here. So the signal comes, it inverts, comes, inverts. So I can see oscillatory waveform. So I'll crank till that oscillation fails. Okay, then I'll say, okay, this is how it is. Now if you look out here, there are two cases. I can have my pulse width for my latch to be so narrow that pulse width is less than the setup time of the latch. Another case is pulse width is larger than setup time, and based on that the timing constraints are a little different. So a kind of a very convenient way to view and think about a lot of these clocking problems is to think of it in terms of a phasor diagram. You might have studied phasors, at least those of you from electrical engineering, in your machines and some of those kinds of where you have AC signals, right? It's not exactly the same, but kind of very analogous. So what we are doing out here, because clock is periodic, a circle is a good representation. So what I show on this here is I choose one clock as my reference clock, one clock edge. So I choose my rising clock edge as my reference here. And this is a 2 pi radians. The rising clock edge keeps happening at this exactly the same point every cycle. Okay, because this diagram is drawn with reference to the period of the rising clock edge. Now the falling clock edge happens a little bit later in the phase diagram. Okay, so 2 pi corresponds to one period. Any other delay is delta by period times 2 pi. That is the angle in radians, gives me the location of that edge. So this is my, and then my T setup. If I want to meet timing, I need my signal to come and arrive at T setup before that. So now what I do is, let us say I set it up where my delay is very small, the logic delay. Okay, so the clock, as soon as the positive clock edge happens, the latch becomes transparent. The data flows through the latch, there is a TD to Q, then it flows through the logic, which is TPD, and then it waits. And then the next time the clock edge comes, again it flows through, goes, waits. So now how much can we increase TPD? And still everything has to work properly. Really I can increase TPD till I come here, right? This green line has to come back and fall on this horizontal purple line. That means TPD plus TDQ can be at most clock period in this kind of a setup. Now let us take the case when T setup is much larger. Okay, I have drawn the same thing out here. I have a very narrow pulse width. This is the rising edge, this is the falling edge, and T setup is here. Again I do the same thing. As soon as rising edge comes, the data comes out, then it propagates, then it waits. And again the next time the rising edge comes, it goes, and so on. Now this data can, as I start cranking up the delay, this edge can only come up till T setup. Because if it comes a little bit later, it will fail, right? That is the definition of T setup. So what it means is TPCQ plus TPD has to be equal to, not T setup, right? T setup minus TPW. TC plus T setup minus TPW, right? So that is the equation. So with this, so that's basically what we have. And then of course, as I said, okay, so I have not written the equation, but these are the equations you can look up in the text also. So hopefully with this, it will become clear how those equations can be explained. Now, one of the advantages of this pulse clocking is what is called time borrowing, which we kind of alluded to in the last class. So, let us say, take this example where TPW is bigger than T setup, right? And I'm kind of I want to be a good citizen. The data launches at the rising edge, and is supposed to get captured at the falling at the next rising edge. I am allowed 1 period. I'm a good citizen. I just take exactly 1 period of time. But what happens is that, so that is what each pipe stage does. But when you actually lay out the design, you finish your layout, at that time the wiring lengths can be a little long, etc., etc. Things are not exactly the delays, because you don't know the exact delays when you're doing schematic, because you don't know the wire lengths, you don't know the capacitance. Only when you do the final layout do you know the situation. And now when that happens, it can happen that this clock period is a little bit, the delay out here is slightly more than the clock period. Of course, it's very much larger than clock period. You just have to go back and redo your layout or redo your design. But if it is slightly more, you can say, look, hey, in my next cycle, my really setup time is reference with respect to the falling edge. I have this much time still available, because when this edge happens, the latch only becomes transparent. The data can still come in a little bit later, till the setup time, and it will still be okay. So I can borrow time from this is supposed to be time for the next pipe stage, but I borrow time from the next pipe stage. Hopefully the next pipe stage is okay. Okay, if it is not okay, if you push that, then again you have a problem. Of course, you can push that and borrow from its following pipe stage and so on. So you can have multi-stage borrowing. So that is where this analysis of, and eventually it might work out okay. So analyzing time borrowing can happen across multiple stages. So analysis of that can become quite complex. But in search for speed and quick time to market, these are things one has to do. The reason quick time to market is because when something like this happens and you do a reanalysis and you say, look, it's okay for me to violate timing a little bit because I'm going to borrow time from the next stage. You say, if I'm fine, design is okay, you change it. You kind of ship it. Instead of redoing the layout, because that process of closing timing can be very time consuming, because physical design goes back. Sometimes if you have to go and change the complete microarchitecture, change the pipe stages, that can be the worst, because it will take long time to again go back and converge. So that is where this also has some benefit. The amount you can borrow is pulse width minus T setup. This is the amount you can borrow, minus, to the extent skew and jitter and so on will reduce the amount of things you can borrow. Yeah. Yeah. The whole time is basically from the clock edge, which is capturing. In the latch, it is the falling edge, with respect to the falling edge, because the falling edge is the one which is causing the latch to go from transparent to opaque.
So, the whole time, the clock should be transparent.
So this is what we are seeing. There is a min delay constraint. So what happens with the min delay constraint is that here this is the launching FOB, this is the capture FOB, and there is some logic through which it is going. We want to see what there is a constraint on the minimum delay of the logic. The logic better not be too fast. If I just have a piece of wire that's too fast, and things might fail because of hold time violation, because the data gets launched by this edge and this guy's falling edge, with respect to that there is a hold time defined. So the data better not come before this hold time, otherwise it will mess up, because then this guy was supposed to capture the old data, will capture the new data. That you don't want that. So the minimum propagation delay from this flop and this has to be at least hold time plus the pulse width. So you see, time borrowing allows you say, look, I want to do more time borrowing, so I'm going to increase my pulse width. It also turns out, I have not discussed here, but you can also hide some of the clock skew by the same reason. For example, if this clock comes a little earlier, this edge comes a little earlier, it is okay, because there is a transparent phase out here. The data comes and it will still make it through. So it has some skew tolerance. So my clock, I am able to tolerate skew up to TPW minus T setup. Dotted line, no, because in this it's a positive transparent. So when clock is high, it's transparent. Clock is low, it is opaque.
Actually, in that time the data should be available. So it is not available, then the extra time of the clock will be used for transmission. White time should be the data.
The falling edge is the one which is capturing the data. So the data better be ready and stable. That time? No. I cannot, if I go in there, then it will not capture it properly. Falling edge is capturing, yes. So I have this much time available for me to capture. But of this much time, I cannot use because it's the setup time. So I am just left with this much time. Yes, if it comes here, it will go through. But if it comes after the dotted line, it will not go through.
Is it like the data should be maintained constant?
Yes.
Even the clock should be
No, clock should not be. Clock edge is happening. All this whole time is saying is, with respect to the clock edge, how much time should the data be kept stable? Remember, whole time can be negative also, as we discussed in the last class. But here I am just showing it to be a positive number. So,
data should be
so increasing pulse width allows you better skew tolerance and borrowing, but then it has this problem that your whole time problem becomes, it will degrade the whole time problem. So that means you have to put more delays out here. What does putting more delays mean? You have to put more buffers. It increases the area overhead, increases the power overhead. Okay. Pardon? No matter what, if you increase the pulse width, what this is saying is I am not concerned about positive or negative value of t-hold, but if the point here is if you increase the pulse width, you have to increase the min delay constraint goes up. By playing around by putting delays in the clock path. Remember, if you put delays in the clock path and the data path, you can kind of move the whole setup hold window. I'm saying if you look at the flop as a black box, inside you might have buffers and so on and extra delay. So that can cause with respect to the arrival time of the signals at the boundary of the flop or the latch, the relative hold time and setup time can be shifted left or right based on internal delays in the data path and the clock path. By the way, a lot of this stuff is in chapter 13, so please make sure you read up chapter 13 also. And a lot of the stuff is not there in chapter 13, but so you look up the video if you have missed tell your friends to look at the video. Pulse generation. So how do you generate the pulse clock? Here is a simple way. You have the global clock signal coming in. Remember, again we are going back to the global and local distribution. Here, so maybe you could have a pulse clock generator here in the local region, right? The global clock comes, it's just a normal 50% duty cycle edge, and then locally you generate the pulse clock. So when the edge comes, you have two paths. One goes directly to the AND gate, another comes through the delayed, it's a delayed inversion, X. So G clock goes high, after some delay X goes low. But for the duration, a short duration, both G and X are high. That means P clock will be high. And then when G clock goes low, of course after some delay X goes high, but then in this overlap, anyway it's an AND gate, right? P clock will remain low. So only during the positive rising edge of G clock, you have a pulse. And you can control the pulse width by playing around with this delay chain. You can put more delay, less delay. You can have tunable delay, etc., etc. So you can control the pulse width. You can also think of how to modify this to allow gated pulse clock. Okay, how do you do that? So you can think about that.